Great. Okay, well, welcome everyone to our second survey paper presentation of the day. I'm Dan Molzon, Georgia Tech. I have the pleasure to introduce the team that wrote our second survey paper titled Big Data Analytics for Future Electricity Grids. So this is Mladen Kezunovic at Texas A&M University and Pierre Pinson at DTU. Now I charged Mladen and Pierre with this very massive task of writing a paper on big data analytics. It's a big problem to survey big data analytics. And so they went out and formed a team with Zoran Obradovic at Temple, Santiago Grijalva at Georgia Tech, Tao Hong at UNC Charlotte, and Ricardo Bessa at Investec in Portugal. And so they have the floor now for about 50 minutes, and then they'll be happy to take questions. And I'm looking forward to a really robust discussion after their presentation. So, Mladen and Pierre, why don't you take it away?
Okay. Thank you, Dan. I want to thank at the beginning the co-authors and the reviewers for their input, but most of all to the organizers for inviting us to do this. This was really enjoyable effort and hopefully productive. So the presentation will be given by two of us, myself and Pierre. I will be going first for a few minutes and then Pierre. This is our outline. We want to set the stage first with the background and then talk a little bit about general importance and feasibility of big data analytics in smart grids, and then focus on a few applications. That's the point where Pierre is going to take over. Now, this is very important. We were discussing a lot what should exactly be the objective of the paper. And we decided to discuss the complexities of these opportunities to use big data, and then reflect on some practical issues and business cases based on our experience, and then offer some examples how these new solutions are realized for creating new business value. What we did not consider an objective was to just do an elaborate comprehensive survey. So this is not that. There are some other papers that are doing that. We didn't look at this as a general scientific area to try to give some guidance across because, as you know, there are a lot of papers in this area and others been doing that. And then we did not go over the entire spectrum of applications. We only selected some. So this paper has somewhat narrow, if you will, scope based on this, what I just explained. Here are a few papers by others. There are survey papers. What's interesting, the area is relatively new in terms of applications of big data in power systems. There were some papers as early as 2013, but most of the survey papers came around 2016, 17, 18. And there's an emerging field, a lot of papers published as we speak. I think at PSEC there would be a lot of papers on this too. I saw some. So this is how we organized our paper. So this is your basically outline of the paper. We want to spend a little time here on discussing the importance and feasibility of big data and clarifying a little bit what we mean by big data, and then certain challenges in doing that before we plunge into applications and some conclusions and so on. This is all driven by an experience that resolving different issues associated with data before even going into applications is a huge task based on our experience. As a matter of fact, you know, probably 80% of the effort is spent on managing data, understanding data, and so on, and maybe only 20% on developing an application. And so we want to emphasize that, and we want to share some experiences that come out of that process. So let's talk about that. Let's talk about data sources that are new, data properties, data management, some of the data science foundation, engineering aspects, decision-making aspects, and so on. The first thing here is that as we look at all of this, there's new data that emerges for power systems applications. It's not new data per se, but hasn't been used necessarily widely in the industry. Utility measurements, of course, are within the utility perimeters, and those are used, but additional data, mostly weather data, even animals, migration data, like you have here in Texas, squirrels, the data about vegetation, the data that can be observed through the drones, the data that represents in GIS format, seismic data, fires, even the social media data. That's all relatively new. And the issue is not to dwell on the data per se, but the issue is there a new value in new data in terms of the applications? So that's the issue. So I'm trying to illustrate something here with this slide that I will explain about big data. The big data implies by the word that there's a large amount of data, but it's not the only problem with these sources. There are a number of other problems, and I picked up here the example of the synchrophaser PMU data, and somebody started out there in the field this game with the words to describe the data that start with V, so we call them V's of big data. And if you look in the literature, you will find maybe 10 V's, 12 V's. We went through the exercise, and here's 16 V's if you wish. And what's interesting here is that it's all real. This is coming right out of a project that we are doing as we speak, and realizing these properties of the synchrophaser data. So I will just run briefly. Volume is clear, large number, velocity, this is streaming data. Variety, you would say, what's variety out there in synchrophasers? Well, there are different vintages of products. Veracity, there's an error defined by the standard. Value, in terms of which application you are addressing, what is the cost benefit of that? Validity, a lot of bad data. Variability, the responses of PMUs under dynamic conditions, not the conditions for type tests, but for application tests, are not defined by the standard. So the data does vary in that area. Venue, they can be anywhere from transmission, generation, distribution. Vocabulary, in the definition of the messages, semantic and syntax may vary. Vagueness, logs that are typically provided by the utilities have different labels for same events. Verification, vulnerability, visualization. Vicinity is an interesting one, and that is, what is the spatial displacement of PMUs in the grid and with respect to an event? So if you have a grid that has 5,000 buses, for example, like ERCOT roughly has, our Texas operator, and they have about 150, 200 PMUs, obviously the placement is sparse. So if you're trying to identify local events like faults and analyze them, the fault may be just there where the PMU is, or far away from any one of those. So you can see that the big data issue is not just about the size, it's about all these properties. And even on a relatively simple application as this one, but very important application, it gets really complicated to deal with this and integrate the data and find the methods to analyze the data. So you have all of these data management activities that are very relevant. They are listed here: data analysis, capture, migration, and so on. And on the right-hand side is an illustration of the details when you start looking at just some properties, like variety and velocity and volume of the data that comes, for example, from land-based stations for weather, radar-based, satellite-based, specialized networks like lightning, weather forecast data from government services, ecological mapping that you need for trees, for example, near transmission lines, different vegetation maps, and so on. And as you can see, the temporal resolution is different, the spatial resolution is different, the accuracy or inaccuracy is different, uncertainty, errors, all of that is different. And so integrating this for an application is a challenge. Now comes the foundations and engineering aspects. And I'm sorry for these pictures. They are Christmas-like pictures, but they do have 3 steps here. One is the data science, that we are kind of looking at, and it has different aspects. And then in the middle are actually the tools, engineering tools to implement the data analytics. And then you have on the right-hand side the portals for the users. So it gets, again, rather complex because, for example, you may be using a multitude of platforms and tools, and the same data may be used by different users for different purposes. So the processing on the same set may have different outcomes. Now, in terms of the data science, we don't see this as something that our paper particularly dwells on. We just kind of put it in there so that we all know that we looked at that. And we look at the data science life cycle from pre-processing, cleansing, importing data, finding the patterns, feature engineering, discovery of features, interpretation and visualization, very important part. So the challenges are high dimensionality in the power system, heterogeneous data, some partially observed, some noisy, some distributed, some streaming. So the analysis has to be matched from time series forecasting, sequence of event analysis, spatial, temporal, network-based modeling, and different techniques. And there are some techniques that we have listed here, and we're using some ourselves, some are used by others, and they are referenced. So this is another spectrum here that exists in the approaches that one can take to implement an application. So now comes the engineering aspect. And I just took this example of the risk assessment and prediction. And the point is, when there is an application on a huge amount of data, it is typically something that a human cannot really comprehend in the original form. You saw some of these sets of data that I have in that table before, and all of that data is used in one application, for example. There is no way of an individual viewing all of this, or even having, frankly, an intuitive feeling how everything comes together and gets correlated. So visualizing this is very important. And one option is to visualize risk. And visualizing risk is not the end of the story, as you know. The risk in itself doesn't mean much. But if you have an optimization technique to mitigate the risk, then there is a meaning to doing something based on this information. So this particular set of drawings here, or pictures, is related to the steps in the risk that is defined by some standards. So there's a hazard component, which is to the left, and it's primarily in this particular case related to the weather. And then in the middle, there's a vulnerability, which is a conditional probability of a failure, let's say in a network based on the weather condition. And then once you multiply that, you get the risk map over on the right-hand side, which is a compound of the hazard and vulnerability. And obviously, in this case, it's related to tree trimming and faults related to that. So you have areas that are most vulnerable with the highest risk. And so you can develop different mitigation strategies. Some may be to trim trees with the purpose of reducing the budget. Some may be related to trimming trees to reduce indices, reliability indices, and their impact on the customer. So the objectives may be different. This is the general framework. On the left-hand side, you will see the risk assessment, elements at risk, risk mitigation, risk threats. And on the right-hand side, the hazard vulnerability and calculation of the risk. And in the power system, we have different components. So there's a whole framework that may be developed for the entire power system and then used individually for certain applications and certain purposes based on the options for minimizing the risk. Now we are going into applications. I have only a few more minutes here. And I picked up asset and outage management. And what these pie charts are showing are typically the distribution of the reasons for failures in the grid. And the reason why we have multiple pie charts is to show that irrespective, whether it's a US, for example, average, which is on the left-hand side, or it's in certain areas like Wisconsin to the far right, or Alaska, or some other areas, that basically it turns out that the weather is a huge impact on the outages, and after that, the equipment failure. And there are some other impacts of animals and so on. So that this begs for an understanding of how the weather may impact and how the failure of equipment may impact. And that immediately drives you to these outside sources, outside of the utilities, and to these diverse sources. So that's how you come to that conclusion that all of these sources matter. These are a few examples. The papers are listed, in this case, on the left-hand corner down. It's going to be presented at the SIGRE in Paris. This is the transmission outage prediction. This is done with the logistical regression. And the first chart to the left is the ground stations, weather stations in the state of Washington, in northwest of the United States. And then there are predictions of the faults when there's no outage. As you can see, there are no false negatives, and when there are outages, they are directly pinpointed, and there are no false positives. The ability to do this in this way is based on a variety of data that is used. And incidentally, some ask a question often when you do these big data projects, how do I get the data? All of the data for this project is publicly available. Everything is publicly available. You just have to know where to go and what to do with it. So that's that. There's another example that is interesting on the failure of the insulators on the transmission line. And the reason why it's interesting is that the little graph up here on the left-hand side shows nodes of this particular processing network that is used here. And the elements of the network are both physical points, which are substations, as well as ground stations for weather. So they all go into this calculation of the BIL, which is the index for insulation strength that you calculate. So you calculate the new BIL based on weather and conditions that are related to lightning current, temperature, precipitation, humidity, pressure, and old BLI. So as you can see, a lot of stuff goes into estimate of the strength weakening of the insulators. And you can have, based on that, the risk hazard map, the vulnerability map, and on the right-hand side, the risk map. And it shows some of the insulators, and you can zoom in, some of the insulators that have high probability of failure. So the mitigation in this case may be the placement of the line surge arresters to actually help avoid failures of the insulators. The next one is the tree trimming problem, which takes in the United States millions of dollars to take care of. Again, the most interesting part is the type of data that goes into this. The trees and the type of trees and their growth rates, and depending on the species and humidity and soil and things like that, which has never really been used before, but it's very, very logical thing when you start thinking about these things. The problem is, how do you integrate all of that? This is also quite interesting. This is an example from Korea. And you can see in the left-hand side the entire Korea, and in blue the region that we are talking about. So in that region, I just set my alarm here, so it's telling me that I'm close to the end, which I have, I think, one more slide. So what's interesting about this is that in that region, which is called Yeonnam region, the sixth one from the right-hand side going to the left on the transformer chart, number of transformers, 247,000 transformers. So this is trying to predict the failure of the transformers. What's interesting is the failure is predicted with a fairly high, on the right-hand side, fairly high prediction probability. We predicting 190 out of 214 failures accurately. And there is no electrical signal in this at all. It's all environmental signals. This is interesting. Why? Because it's telling you that the data-based models are not related to the physical necessarily in this case. But if you combine the physical models and the data models, then you can go into the root cause analysis. And so there are additional benefits of doing that. But this is much cheaper to do than to rely on various sensors, particularly on the transformers in the distribution, where it doesn't justify putting all of these sensors. And finally, this is my last slide. I'll turn it over to Pierre in a minute. This is about synchrophaser applications. We moved this one forward so that I can talk about that. The only point I want to make in interest of time is the right-hand side diagram that shows the event analysis first, and then event classification and event prediction with applications in asset management, outage management, operation, and planning. So as you can see, the synchrophasers, whether they are used in transmission or distribution, they have a huge potential to be used in different applications. But as I said, a lot of issues in merging the data, and also one of the things that we notice that people are doing for no reason is they are not correlating the PMU data to some other data that is extremely valuable in assessing the events that are detected by PMUs. So I will stop here. I think I took about a few minutes here. I hope I'm within the time. I'll turn it over to Pierre to continue. And Pierre, just let me know when you want me to move the slide forward.
I will just say next, I guess, something like that. So thank you very much, Mladen, for this first part of the talk. And as we were saying, thank you to the co-authors, and thank you to those people who invited us to do this work. It was a lot of work. As you can see from this presentation, there's so many things to cover, so many things to say. So we're trying our best to give you a condensed view, and really you can look at the papers and all the links we have in there if you're interested to see more. I think there's 258 references at the end of the paper, and we've been selective. So that really shows how much there's going on there. So, I mean, I think this here, the transition is perfect. I see personally PMUs and smart meters as two of the, let's say, devices that has brought the needs and the feeling to work with big data in power system applications, maybe from different angles, obviously, and different type of applications in mind. But it's a classical case of spreading some devices that's just going to take some measurements. Maybe you're not so sure of what these measurements are going to be for at the beginning. Thinking of the European case, it's maybe more made for settlement, but then you realize there's so many interesting applications from using this data if you can build this big data layer in between the measurements and the collection of the data and the applications to create value, right? So the smart meters today, I mean, there's a very high penetration, and it's planned to have, 100% penetration of smart meters, if possible, in many parts of the world. The data from smart meters today doesn't have really the granularity that would make you say, okay, that's really big data in terms of high temporal resolution. Granularity is typically between 15 minutes and 1 hour. But I know, I mean, it is the case, at least in Europe, and I know also some cases in the US, where people would like to develop their own little smart meter plugs so that you can get very high resolution data that can be for peer-to-peer markets that are very trendy right now, and that can be for other type of application. So what we're saying is that it's very interesting to produce this data and to have data from these smart meters. Really, where it becomes interesting is where this data is combined with something else, or where we see what we can do with this data. So I have an example also there from my experience in Denmark, is that we've been discussing a lot with colleagues, what if we combine the data from the smart meters with transportation data? Because we can actually get data also from all the transportation system in the Copenhagen area. And then maybe by looking at these two data sets together, we can do even better things in mapping what's going on with consumption in the city of Copenhagen right now, and let's say for the next few minutes also, right? So it's just one example. Next, Mladen, please. Right. I think this graph here is also representative of what I was just saying before. You just think of smart meter data collection, and then you realize, oh, see, if I combine with this data from weather, if I combine with GIS data, if I combine with some, I don't know, historical data and prices, some other type of static information about the consumers, then we see there are many type of applications. And I have to say, really what's a pleasure is that over the last 10 years, let's say 15 years, we've really seen at different conferences, new applications popping up, new interesting, I'd say, value added from the analysis of the smart metering data. And here you have a set of applications. I'll discuss afterwards some applications that are quite obvious, like load forecasting. Demand response also has become obvious. You know, when we have smart metering data, we can do a lot with demand response. There's I said peer-to-peer markets, right? I see there on the right in the middle, applications 13 and 14. You can see I find this application a bit more exotic, and this is typically applications that people, I think, never thought of in the first place. And now that we think of it, it's just obvious that these are extremely interesting applications. So the first one is DR detection. Today, many of the DSOs would say, oh, I would love to know if people have bought an electric car, if people have installed a heat pump, because in principle, you would like them to declare it to the DSO, but people don't because they're not obliged to, or because they just don't care. And so a lot of DSOs would love to have applications where we can just detect DERs or electric cars, heat pump, whatever, based on the streaming of data from smart meter, maybe coupled with some other sources. Another one, which is the application 14, is theft detection. And I remember seeing a very nice paper from Greece, from NTUA a few years ago. I think it was the last PSCC in Dublin. It's a very nice application. Hopefully it's not that relevant everywhere in the world, but it's clear that in some places, certain DSOs are very interested in analyzing the data and knowing if some people are not trying to cheat with the system. Then you can see here, you can look at the slides maybe later and see a lot of the applications that are possible, and I will cover some more anyway a bit later. Next, Mladen. Right, so load forecasting. Next also, Mladen, I think there's some things that will appear, and next, you have to press twice more. Okay, good. So load forecasting is something that might be one of the oldest application when you consider data in power system application. And it has really evolved a lot and really embraced what's happening with big data. So that's why we thought it's something to show here. Typically today, the load forecasting problems It's for many type of stakeholders in the system. I mean, the retailers are interested, the system operators are interested. Even as I was saying, if you have peer-to-peer markets, you might have people that are interested in the consumption of their neighbors in the future and want to predict that, right? Here are two examples on the left, trying to predict future annual peaks. So that can be for considering, I don't know, some capacity consideration. The one at the bottom is about the load for next week. This could be also for some scheduling problem. And there on the right, you have this correspondence between different type of timeline. So from seconds to decades, and what type of problem that may be involved. And you can see that whatever the time scales you're interested in, whatever the application, really load forecasting is one of these fields that is evolving a lot thanks to big data. So next, Mladen. Right. So what people have been doing, and I think it's a nice example that we have also in the load forecasting area. When people collect a lot of data, then you have to try to understand, you know, what's in there. So you will have some selection problem if you have too many features. You will have some problem with combining information, and then you have problem most likely with dimension reduction. So here, typically, you see a lot of data points, and you have a relationship between the load and the temperature. And that's where we're going to bring some models to reduce the dimension and find some kind of relationship that will faithfully represent the dependencies between temperature and load. That's the simplest relationship you may want to look at. But you can see this relationship is really dynamic. It can change depending on the hour of the day, depending on the season, etc. And then, as I was telling you, you could bring some other data for transportation, human activity, etc., to help also model that. So next slide, please, Madam. Another aspect which I think is very important and covered in many works that we see at PACC and other places is that with more and more data, we also have the possibility to look at all the processes and the predictions, etc., in a more probabilistic framework. So here you have an example. This is something that has changed a lot in load forecasting over the last decade. Today, it's quite natural that you will make a probabilistic forecast for the load. And here you have trajectories for the monthly peak forecast for the coming year. It's an old peak, but it's representative. And you would have a central trajectory, which is your expected peak or the median peak. You may have some intervals here between the solid gray line and the green solid line. And you may have also trajectories that are given by these dashed lines, right? So it's very important to see that in a lot of these big data method, big data applications, now we try to work in a probabilistic framework. Next slide, Mladen. Thank you. I was telling you about the problem of feature selection, and there also in load forecasting, it's been something that's been in the air for quite a while. As I was telling you, you can get data from so many different sources about human activity, about the weather, etc. And here what this GIF shows is how you may focus on selecting data from different type of weather stations, depending on the area you care about. So here the area that's popping and varying is the area you want to forecast for. And then these little stars that are becoming orange, it's the weather stations that you would select for doing forecasting. And they could change with time, they could change depending on the quality of information. And you really have to think about this feature selection in a very, very dynamic manner. Next slide, Mladen, thank you. The final thing that I thought Mladen would insist more on, but we have so many things to discuss that maybe we cannot cover everything. It's also the fact that now that we collect a lot of data from different sources, we know there's going to be latent dependencies between the data, and then we can actually use these latent dependencies for also checking if the data we have can be trusted or not. And again, in load forecasting and load modeling, it's something that has happened for quite a while, because when you get your load data information, you can actually look at the dependencies with the weather data, and you can actually see if the weather data that you have can be trusted or is erroneous, or I don't know, if there's been a drift in the dependencies between the two. So we have also to profit of this big data setup to analyze the redundancies and also check the data, clean the data, etc. So really this field of load forecasting has a lot of the nice features that we see in the promise of big data for power systems. And it's nice to have these examples there. So next one, please. The other one, on the other side, not for the load, but for renewable energy, in the analytics and forecasting side for renewable energy, there's been a lot happening over the last 10, 15 years. And there it's really the type of data sources, I think that is a game changer. And we have to recognize that it came more from the solar side. You see on the top right, it's a picture for a solar power plant. And you have this sky cam or sky imagers, right? And then there's something really new, you know. Today, maybe for us it's obvious, but at the time, this guy said, okay, we have time series for the production from these PV plants, and then we have images. And when you do some modeling, you have to relate images to some time series. Now, obviously, with CNNs, etc., it sounds obvious, but at the time, it was a very challenging thing. Same story for wind, the peak that's just next to it on the left. It's a weather radar installed at an offshore wind farm. And it's a bit of the same story. You can have weather radars today. There's some that are operational in the UK and some that are more for research projects. But you receive images that tell you about what's happening around the wind farm. That can be 30 kilometers radius, 100 kilometer radius, depending on the type of radar. And that's really a lot of data to process. You have to find the clouds in there. You have to look at how they're going to move. There might be also some detection of waves there. There's so many things you can do with these images, but it's overwhelming playing with them. Another one, which is at the bottom, is this LiDAR. So it's a laser type measurement technology. And today they are putting this laser type measurement technology on the turbines to see the wind coming somehow. And same story, it's very big data you get out of that. Finally, you have this peak on the left because it's not only measurements, but it's also forecast. It's always been in the air that we want to have higher resolution forecast, but it's really happening today. I mean, it's happening at the global scale. All the Weather Institute, the Met Institute are trying to increase the resolution of the models. But since meteorology has been kind of liberalized, you know, you can have a meteorological model on your laptop and run it. You can also today run very nice models on GPUs and profit of the power of these GPUs for having extremely high resolution weather forecast. So it's an example here of a small company we work with. They have super high resolution forecast, and typically it's going to be the spatial resolution is in meters, tens of meters, say. Also, you have all these vertical layers. And then in terms of temporal resolution, you can have a 30-second time step for your weather forecast. So it's really overwhelming to get this data. And actually after, it's a big piece of work to sort what is signal, what is noise from this data. So there's really a lot of happening in this energy analytics and forecasting field for renewables. Next slide, Mladen. Another thing that we didn't discuss much so far, which is more of an opportunity that we'll see towards the end, is that there's so much data flowing. We can also think of new business models. And I think it's something that's discussed right now in renewable energy analytics, but it will be the same with smart meters, for instance. I've had discussions with different companies, utilities, system operator, about what's going to happen in the future with smart metering data. What if people say, there is value in my data, if my data is shared, I want to be paid for it? And we could generalize this idea in a big data framework. If people were to share information, then we could have a marketplace to reward people for sharing data. So here we have a setup for renewable energy analytics. For instance, if there are some people sharing radar images, weather forecasts, power data, then there could be a payment. And this idea of a marketplace could also be generalized to collaborative analytics. So if you do distributed learning, federated learning, for instance, there is maybe a reason why you should pay others to help you improve your forecast through this collaborative analytics. Next slide, Mladen. Thank you very much. Oh, next one. I saw this one was repeated. Next one again, Mladen. Thank you. Right, so another topic, so this was prepared by my colleague Ricardo. You should go through this slide from top left to bottom right, okay? This is another topic, which is energy optimization and efficiency. It covers a lot of subtopics. There's really a lot happening related to big data for this kind of application. But typically the starting point, so it's what you see on the top left, is if you work with utilities, with DSOs, you will hear always similar stories, you know, the way they think of their relationship with customers, how they characterize them, it's really static. You know, their typical load profile, the elasticity is really based on some basic correlation calculation. What we call here non-intrusive loads monitoring is actually not what you may think of really. It's just some basic idea of what are typical profile for appliances that are just combined in a heuristic way. And then whenever they do optimization, they just overlook actually all the value in the data, right? So on the right, you have there what we consider are the contribution from big data. Really, you can avoid the full modeling of all these physical systems and the constraints that can make things much easier. If you were to implement solutions, so think of demand response, for instance, and you have control policies for demand response, you can really do it in a continuous and data-driven way, so it can improve all the time. You can also make it cheaper with online learning, right? And then what is very nice is that with this big data framework, you can also merge a lot of data sources. So you can combine the data from your smart meters, but you can also combine with data that will come maybe once a month or once forever, etc. Finally, which is something that we don't do enough, maybe for power system application, but it's really picking up, it's transfer learning. So when we are learning for certain consumers or certain assets, we can actually use what we've learned from these assets or customers and use it as a warm start, you could say, for some new assets or new customers. The big data use case examples on the bottom left, I mean, there are many, and I will zoom in on the next one. But really, you could think of all these applications related to non-intrusive load monitoring, demand response, online customer profiling, and also looking at energy savings applications. There are a lot of open problems there, actually, mostly related to this data availability. But then there's also, and sharing of data. I was talking about that earlier. I mean, GDPR for us in Europe is an issue, for instance, and there might be interest to find ways to do work without having the data shared with everybody. And finally, we would like to integrate better the human behavior, and that's where we would bring some kind of behavioral economics layer into this big data methods. So next slide, Mladen. Okay, a typical example, there are so many, but reinforcement learning is something that is becoming more and more natural for many applications. This is an application that Ricardo shared with us about some pumps for a wastewater pumping station. And you could look at using reinforcement learning in a big data context for optimizing the policy for the wastewater pumping station. But you could think of it in the same way for any kind of demand response, some coordination problems, some storage operation, etc. But here, what's really interesting with this kind of setup, reinforcement learning, which, yeah, can be used in so many different flavors, is that you continuously use your data from different sources to always track what would be the way to make optimum decisions. Next slide, please, Madam. Good. Grid applications, it's even broader than what we were discussing before. And I'm really going to go quick with this one instead of going into all the details. Typically, the big challenge or the trade-off that has to be made here is that we've been used to look at hardware solution. You know, whenever there are problems, we want to enforce the grid, we need to invest, we want to always have more and more assets. But really with big data, what we can do is try to be smarter about the use of the assets and do things that we thought we couldn't do before. So what's really nice with this big data setup is that now we could maybe have a better balance between investment in hardware and being smart about using optimally our assets. Two other aspects here related to grid application is monitoring. You will see an example after. We have classically, thinking of DSOs or utilities, we had a lack of observability. And today, when we want to integrate DERs at lower level of the system, it's actually really good that we can collect a lot of data and have some kind of observability at the lower levels of the system. So quickly through the various box, I mean, the contributions for big data is really that we can combine heterogeneous data sources. And that's things we said before, I mean, PMUs, meters, social network. Something that is quite new is to actually bring text information. There are some papers appearing the last 5 years to try to combine all the traditional data, you could say, even though they are not so old, these data sources, with text information. And there's really a lot of idea to automate the decision making, to give a lot of support to decision making. And I think if our colleagues from RTE as online, you know, they've even been discussing this idea of, you know, having some kind of automatic operation of the system in the future. Not for everything maybe, but to have more decision support from machine learning, for instance. Some open problems at the bottom right. There's always an issue here with the quantity of data. I mean, it gets really insane when we have all these data sources and we want to merge everything together. One of the biggest problem, I guess, that was discussed on Monday afternoon, is interpretability. If we want it to be adopted in practice, the decision makers, the operators have to understand what's happening. So it's really something that we have to work on. And that leads to this last point, is to mix the physical and the data-driven approach. Next slide, Mladen, please. Right, next. Yes, thank you. So again, an example that was shared by Ricardo. You have here two grid levels, medium voltage, low voltage. And in both cases, the problem is quite similar. You want to have increased observability, you want to do state estimation, and you want to increase situational awareness, right? So on the MV side, you see you can have different type of data sources. This can be forecast, this can be measurement data, and then you want to use that for improving your observability. And on the right side, looking at the low voltage grid, you will have different type of data. Maybe you will have data just at very specific location, maybe only 10% of the system could be covered, and you want to actually deduce some state or some key information about the system as a whole. Right, next slide. Yeah, so we're gonna reach, this is a pack slide just to show you how many opportunities and challenges there are in the field. We actually struggled when we wrote the paper to agree on what would be the right volume of opportunity and challenges that we would like to cover. So maybe we start more with the opportunities first. There are really many. I mean, big data is really contributing a lot to forecasting. I talked about load forecasting, renewable energy, but there's so many forecasting problems that can benefit from big data. I was mentioning, I believe in the future, we need to think better about monetizing the data, because we cannot believe everybody's just going to share data for nothing in the future. And we have to consider how to optimally value the data and the way data is shared. The opportunity is to combine different ways to model also and to think about these problems. And that will most likely make actually the models lighter, because it's a classical case. You know, if you only go data-driven, you don't bring any kind of information about the system, and the models become overly complex. But as you bring physical or expert information about the system, you can have models that are much lighter and actually more efficient. There's many applications that may want to be considered, and we believe the value may be huge. So we need to invest more in various applications and showing what's the value from big data. And the last point here, it's about replacing some of the tasks performed by operating agents and experts. This is an opportunity, but actually it's also a challenge. I think if you go talk to these experts and these operating agents, I think they will not be very keen to be replaced by algorithms. And I was talking earlier about interpretability. I believe also this will be an issue that there will not be adoption until it is fully interpretable. So some of the challenges, we have discussed, or Mladen was showing this point about data sources. We would like to see more data sets that are available for people to show the practicality of their methods, to develop new methods, also to reproduce each other's work. So we hope there are going to be more and more of these data sets available in the future. The data should be open, right? And there should be also benchmark models so that we can really help advance in the right direction with the development of this big data approach. There's one point also about the evaluation. It's something you can see in the literature where you compare the different works. It seems a lot of people are using their own metrics, their own ideas about evaluation frameworks, and that being the quality of the work or the value of the work, right? So we need also a lot of thinking about how we agree on quality and value assessment of using big data. There's some last points here. I think the most important two I will insist on is the computational requirements. I mean, most of us are very happy to develop approaches using big data, but then we realize there's a bit of a gap between what we do in research and development mode and using it for real in industry. And one of these gaps will be the computational requirements. Typically, some of the methods we develop will require a supercomputer, but then if you go see a DSO or a utility, they don't have a supercomputer. So you have to convince them to run this on Amazon or something else, and it might be a bit of an issue. So finding optimal trade-off between centralized and decentralized approaches might be a way, but I think we have to be a bit inventive in terms of how we're gonna try to keep it to a manageable level in terms of computational requirement. The last point, I believe, is one of the most important, is cybersecurity and privacy. And there, the focus has increased a lot over the last few years, but we can see in different countries, it's becoming more and more of an obsession, both cybersecurity and privacy. So we believe there's a lot of more work to be done on these two aspects. Mladen, the last slide. Thank you very much. So to conclude, yes, I wanted to insist again on how nice it was to work with these co-authors and to be asked to produce this work. It was really a lot of work, but hopefully the paper, you will like it when you go through it. We addressed, we hope, everything related to big data analytics and the application in electricity grid. As Mladen was saying, our point was not really to dig in the methods, to give really an overview of the mathematics involved. We wanted to be really broad and cover everything from the basics with data science, engineering consideration, and going towards application. We had a review about some interesting domains. We don't say we've covered all the domains, but still I think it's some of the domains where we have some of the most representative advances with big data analytics, and hopefully that will help with momentum for the other domains. We gave some example about the recent trends, and we formulated some recommendation or we discussed these challenges and opportunities that I just mentioned. And then, yeah, we try to be, I'd say, fair. We try to find the right trade-off. How many references can you include in this kind of paper? There could be 1,000, but maybe that would be too much. So we try to really keep it compact. And there's this 258, I think, references that we try to carefully select and tell, you know, how you should look at them. And finally, as I was saying, we have tried to do our best to give some direction for future research, and we outline challenges and opportunities. So thank you very much for listening. And I think now it's going to be time for questions. Thank you.
All right. Well, thank you very much, Pierre and Mladen. That was very comprehensive, very interesting. I know I learned a lot. And so we've got some times for questions. I see there's some in the Q&A already. If you guys have more questions you want to ask, please add them to the Q&A, and I see another one just popped up. All right. And so I'm gonna take take the liberty as the moderator here to ask you one of my own questions first. On Friday, tomorrow we're gonna have this panel session talking about how do you translate ideas from academia and from the research community into practice. And so I'm wondering if you could maybe give some examples or a brief discussion on the challenges and opportunities, and how do you take these ideas that you've described here and get them, you know, actually used in reality?
Well, we can one by one comment perhaps, or whoever wants to comment. But one thing that we learned is that you have to, if you want to transfer something to industry, which I guess is a goal, then you need to understand what the industry needs. So this, connection to the industry to discover what their issues are is absolutely necessary to guide the research in this area. Now, at the same time, in many instances, the industry doesn't really know what to do with some of these developments. And so there is a little bit of a confusion at that end. However, everybody would agree in industry about some huge problems that exist. So one should go with this new area and address these huge problems. For example, the outages, at least in the United States, are going up. They are not going down in its frequency and the spread. The losses in the country are about $100 to $150 billion a year based on the losses in power. So anything that has to do with predicting, for example, outages and helping in restoration and things like that is a big area of interest. The assets in the United States, the grid is about $1 trillion worth in assets. Obviously, most of these assets are old. And so anything that can help to maintain these assets and prolong the life and things like that is relevant. And one can go on and on. If one looks, for example, at the reasons for putting the synchrophasers in, original reasons, in the transmission network, was because the dynamics of the network couldn't be observed with the SCADA system. So now when we have that observability or relative observability, there are about 3,000 PMUs in the grid in the United States. The question is, what do we do with it? And frankly, as of today, there are very few applications out there that are actually taking advantage of that. So that's another area. So one could go on and on. I want to give a chance to others to comment, but that's what I have to say about that.
Yeah, someone's ringing. Just a quick comment, because what you're asking, Dan, is very interesting, and I think I'm talking for all of us. You can correct me, the other panelists, but there is also the way we do our R&D work that is very important here when it comes to these data issues. And I think you really need to combine the two hats, being a bit of a consultant for these various industries and being a researcher, so that you listen to them, their issues with data, their issues with application, and you try to be a consultant here, not to make money, but really to listen to them and propose something for their problem. And then, as Mladen was saying, then you profit of this relationship to say, oh, by the way, I just realized you have this data and you have this problem. Let me show you what you could do. So you try to build this relationship for some kind of transfer of knowledge, or pushing them to try some new ideas. And I think, my experience would be that all of us are doing these kind of things, to be a bit in between, the consultant role and the academic role, to make sure that this transfer happens. I don't know if Ricardo, Tao, Zoran want to say something about that.
I can add something. An experience we are having in one project, that we started with big data, and in the end it's with industry. We end with useful data, because you can easily get gigabytes of data, but in the end, when you start looking at the data and the data you actually need to make some kind of decision, you only have some megabytes of data. And I think this is being one of the biggest problems when you have projects with industry, is that big data doesn't mean that you have useful data. PMUs is in fact a good example, because you easily get gigabytes of data every day, that it's a normal operating conditions of the system. So I think one of the challenges, in fact, is to try to understand the value of the data. In some cases, put the price on the data. I see we had one slide on that, and I see also a lot of questions about that. So I think it's more that. So I think the perception of industry on one side is that I have all this data, this is big data, try to bring some value or extract some value out of it. But from our side, we have a different perspective. So I think bringing these two perspectives together is in fact one of the biggest challenges that we have.
Well, you know, Ricardo, I think that's a really good point. And so thank you for all the answers. But to build on your suggestion here, there are a couple questions along those lines. You know, what opportunities do you see from a business perspective regarding smart meter data management, and how do you deal with privacy issues when you're trying to deal with these challenges using big data? Are there ways to have win-win solutions? You know, and how do you set up? You know, you talked a bit about data markets as a possible way around this. Can you maybe expand on some of those issues? And I think that would address a handful of these questions.
Yeah, so I'm going to start maybe quickly and I'll let the others talk. I mean, related to that, I think it's an extremely interesting field because it goes out of our engineering, say, comfort zone. It brings a layer of economics and social aspects. When you think about this data exchange, there's really different angles. You could play a liberal and believe, you know, if we set up a market, then people are just going to be willing to just share the data and there's just going to be a price tag. And most likely this price tag is just going to represent the perceived loss of privacy, right? But then there's the other angle, and quite a few of us have worked on that already. It's to use differential privacy or any kind of approach that permits or that tries to protect somehow the private information from the different data sources, right? So I think in the future, we're going to go into this direction, trying to mix the idea of valuing the information and keeping the information private. And right now, I mean, let's be clear, there's no real business model because we don't have the foundation to show that it can work. You know, both the privacy, I mean, I don't want to be not nice to our colleagues who do that because they do amazing work. I'm just saying in practice, to really show in practice that this privacy preservation layer will actually work for various applications. And similarly for the data markets, it's the same. There are many proposals on the way, but we don't have a demonstration in practice that there would be a viable business model.
There's one comment that I would like to make that we recognized as we were interacting with the industry and implementing some of these things, is that the cost of implementation upfront is high because of this enormous effort in dealing with the data that is not prepared for these kinds of applications originally. You go to a utility, they wouldn't have all of this readily available necessarily. So there is a huge effort to put all of that together, and there's a cost associated with it. So the problem I was mentioning earlier, if you attack an application that has an incremental value and it requires a huge upfront investment, it's not going to go anywhere with the end user. So you really have to attack the applications that have huge financial impact on the utility to justify all of these investments.
I think that's a really good point, Mladen. It sounds like they're not looking for incremental improvements if it's a big challenge to collect the data. And that actually is kind of related to this first question here, where they said, you know, we're going to have increasing amounts of extreme events in the future, and because weather and trees are a big aspect of power outages, that, you know, incorporating this additional data like you suggested initially, Mladen, is potentially a game changer. But they asked the question, is it sustainable? You know, you need big data sets, you need to store the data for a long time, takes a lot of energy, takes a lot of processing power, a lot of money. How much is this a sustainable approach to solving these problems?
Well, first of all, if I may just comment on that, the upfront effort pays off later on when you get everything lined up. So the cost of sustaining a new influx of data over time and utilizing your application is relatively small at that point. So that's one thing. The other thing is, again, the value of doing that. For example, vegetation management, if you just want to take that one application, in the United States, in the areas where there's a lot of vegetation, And there are areas like that around the country. One, I didn't realize this until I started looking into this. People are spending millions and millions and millions of dollars a year to actually trim trees, and let alone to deal with the outages eventually, and have the maintenance crews and so on. So if you are asking a question, what is sustainable? You would ask a question first: is this practice that is out there sustainable, before you even implemented anything else? Because sustainability of your implementation is going to be correlated to the willingness of people to come out of this problem that they have, and they don't know how to solve it, but they know it's a problem. It takes too much money, reflects on the reliability indices for the customer, where they can get additional penalties, and it's just not sustainable to not have a better solution. So that's kind of a hand in hand, for the best outcome.
No, I think that's a really good point, and making that case to the end user is the goal here, right? I think that makes a lot of sense. I wanted to ask the second question here from Gianfranco Ciccio, who he says, with the diffusion of distributed energy resources and corresponding changes in the net power load, how much is past data useful for load forecasting? I don't know if maybe Tao, if you're on the line here, I know this is your area of expertise, if you might have some perspective on that.
So the question is about the distributed resources to load forecasting, the impact of DER to load forecasting?
Yeah, so you have all this historical data, but we're adding DER so quickly. How do you know, how useful is this historical data in predicting future data with, a rapidly changing landscape on the distribution system in particular?
Yeah, this is a great question. At the beginning, so when your distributed resources, the share is small, they are basically viewed as noise. But as you have higher and higher penetration of these resources, eventually they will change your load profile, like the famous duck curve. That's one of the outcomes of these resources. And I consider historical data still very valuable, because that really tells the nature of how people use electricity. We always have those underlying thing out there. We use AC, we use electricity to cook, and those really reflect human behaviors. On the other hand, we can always do different ways to treat this DERs. We can model DER directly, or we can include additional variables to the load forecasting models. For example, recently in my group, we look into some other weather variables like humidity and wind speed, cloud cover, and rainfall, and something else, some other variables. So these other, solar related variables as well. So these other variables can be put in the load forecasting model, and then together they can capture these other active and distributed resources at the same time with the temperature effects. So there are different ways to treat them, but I just received another question a few days ago from a utility who asked me, how many years of history shall we store? And I said, the longer, the better. Because you never know when you will need to uncover the organic load, the real load generated by human behavior.
That's a really interesting response. Thanks, Tao. That's great. One other question from Patrick that to follow up on one of your earlier points, Pierre, that I think is a really good observation. He says that edge computing, by pushing the computations out to compress data and at the edges of the network and send it back, seems to balance or help balance between value and data value and privacy. Which in a sense seems to be a little bit opposite of big data. You're having the computations done on small data and just propagating kind of the results back to a central location. And I know both Pierre and Mladen, you've thought a lot about edge computing as well. And I don't know if Santiago's on, but I know you guys have been thinking a lot about that. Do you have any perspective you might share?
I can say something quickly. I mean, I think it's totally right, you know, and it goes along what Ricardo was saying. You know, we go with this idea of big data. We want to collect as much as possible, and I talked about computational cost toward the end of the talk, and then there's privacy, etc. And then we realize, okay, but then maybe it's not the smartest way, and we need this balance between centralized and decentralized approach, and definitely any kind of edge computing will make sense in the future, so that we control this trade-off between aiming to centralize information and aiming also sometimes to keep it as decentralized as possible. So I totally agree that we have to think it in this more flexible framework of edge computing.
Yeah, there's one point I would like to make about the future architecture, or generalized architecture of the power system that includes both the legacy system and the systems behind the meter. That is not something that is established in the community. We talk about these options of centralized, decentralized, coordinated, and so on, and that's okay at this stage. But at one point in time, one will have to select an architecture. And then the privacy issue is tied to that particular selection. For example, if you agree as a customer that has resources to let the utility actually, you know, dispatch your resources, then you have an agreement with them to get access to your data, and you get the benefit for doing that. If you want to only coordinate, then you may have to have the processing power at your place to be able to share something to coordinate. And if it's totally decentralized, then you are in charge and you're just looking at a market where you can sell your power or services. Now, one thing that we need to keep in mind, and you know, power systems is an area that evolves very slowly. In order to talk about the edge computing, we have to have a, you know, societal push that the edge customers, you know, have the computational power. If you look at the 145 million metered customers in the United States, only a small percent has actually any computational power at their premises, and those are mostly industrials and commercial, and some residential. But a lot of others don't. And so, if there is an architecture that assumes that, it better be something that is affordable throughout the society. Otherwise, it's just not going to work.
Yeah, I think that's a really good point where it comes to the architecture is going to both enable this and be chosen based on what you want to do. So I think those are both really good points. Maybe one more question before I have everyone go and catch the next session, which starts in 3 minutes. So Lena Roald asks, so we know that data can be biased due to particular operational practices of a utility or some specific aspects of a location. How much would you expect methods developed for one area to carry over to other areas or other utilities? You mentioned transfer learning a little bit in your presentation. Are there some applications where this might be particularly effective or areas where it might not work so well?
Well, in the areas like asset management, everybody has this, pretty much the same assets. And so when we developed some of these applications for assets and solar and so on, it was transferable. We were able to, use the same model with some tweak in the other utilities.
I think it's a Patrick question at 6:53 p.m. There's also a key word in there, because in lots of all these systems now, what we can do with so much data and better mathematics these days and computing is really focus on causality, right? And some of the key thing of transfer learning is that you really learn what are the causal relationships, and then these basic causal relationships, you can transfer them, right? And then it will adapt locally to the specifics, but you will know some of the core or the kernel of your problem, and you can just transfer it around. So it's really something, I know quite a few of our colleagues are looking into causality, but it's really something that will help so that we have much more confidence. We can transfer knowledge models to new location, to new setup in the future.
Yeah, if I can add, yeah, so we can learn from other early adapters of big data. Yeah, these people in Google and other industries, they faced related problems. There are some solutions there. Transfer learning is a good example, but there's also multitask learning, for example. So there are multiple ways to formulate the problem, and I think, we have to look from multiple sides.
That's great. No, thanks for all the answers. I'm going to have to cut us short here, even though we've got a bunch of more interesting questions left, because I want to make sure everyone is able to get to the next session on time. But I really appreciate all your effort in putting together the survey and this presentation. I know we really tasked you with quite a challenge here, and I really enjoyed reading through the paper and think it's a great contribution. So I'll clap for you, and everyone else.
Thank you so much.
Thank you.
Thank you. Thank you.
Please go to sleep now, Daddy.
Pierre, it sounds like you're being called.
Yeah, I have another speaker with me. He's a 4-year-old, and I really enjoyed it. Thank you so much.
She gives good reviews too, I suppose. Thanks, everyone.
Enjoy the next session. Bye-bye.